picking up where we left off last week with the summary of the two different types of system, star and delta. We talked about this last week. In a star connected system, line voltage is √3 times phase voltage. So that's where the two dual voltage system kind of comes from in this country, is that your line voltage, √3 on our standard system, 400 volts, phase voltage is 230 volts. And that, so if you do 230 times √3, you'll find that's somewhere around about 400. Yep. Okay. In the star connected system, the phase currents and the line currents are equal, because all the current in a line is going down one phase, then to the star point. You have three line voltages 120 degrees out of phase with each other, three phase voltages 120 degrees out of phase with each other, and each of them are 30 degrees out of phase with the line voltage. In a delta connected system, the line voltage and the phase voltage are the same. So you put 400 volts across a phase in a delta system, but the line current is √3 times the phase current in a delta connected system. Okay, again, there's three phase currents 120 degrees out of phase with each other, three line currents 120 degrees out of phase with each other, and 30 out of phase with their respective lines. So that's a summary of what we covered last week. Okay, so what we're going to move on to now is power for a three-phase balanced load. So for the circuit shown, the apparent power to each impedance, SZ, is the line voltage divided by √3. That turns it into phase voltage. Yeah. Times the line current. So that comes from the formula P is E times I. All right, but it's just showing that it's the line voltage divided by √3. So that turns into the phase voltage here. This voltage. We look at that one thing there. All right. So what you're doing there is you're splitting this voltage into that one, and remembering the result is not half of it because they're out of phase with each other. That's the issue. They don't peak at the same time. Okay? So if we look at it like that, we could apply that same rule to any one of these three loads, and therefore the total apparent power must be 3 times that. Okay? Everyone see that? Yeah? And therefore, that's √3 times EL times IL. Okay? Or not? Okay. In a long-winded way, all that slide has proven is that the total power is 3 times the power in each phase for a balanced load. Yeah. Everybody happy with that? Yeah. So, power for a three-phase balanced load in delta. Here we got the power to each impedance. So each of these impedances, it's the current that's different this time. So we've got a standard line voltage across each of those three impedances, but the phase current, or the current through each of those impedances, is the line current divided by √3. So we're using the I times V version of calculating power. So we're dividing the line current by √3 and multiplying it by EL. Okay. And again, bit of substituting in. Each of them are the same situation because they're balanced. Okay. So again, we end up with, down the bottom, the total apparent power is 3 times the line voltage times the phase current. Okay, there's a warning here that this bit is the same as what we got on the previous slide, √3 ELIL, √3 ELIL. That does not mean that if you connect the same load to the same system in star or in delta that you get the same power out of it. Okay? Because the current is different, will be a different level in star connection to what it is in delta connection for the same load. Yeah? Because if you think of our system, when you connect it like that, each load is going to have 240 volts across it. So if there's a 10 ohm resistor and that's 240 volts, the power would be 2,400 watts. Yeah? Everybody happy with that? In this system, delta, it's the same resistor, 10 ohms, and it's got 400 volts across it. Yeah? So it's going to have a different current and therefore dissipate a different power. But it's still, the total power is still 3 times the line voltage times the phase current. And that still stands true. Okay? Everybody reasonably happy with that? Yeah. So, going to have a look at the problem now. Got this one in your notes. 3-phase motor is connected to a 440 volt line and draws a current of 5 amps. If the power factor of the motor is 0.8, calculate total apparent power, total active power, and reactive power absorbed by the machine. In terms of a motor, you're going to assume that it is, that they've wound up with all 3 windings at least somewhere in the same ballpark, resistance and inductance wise, otherwise that wouldn't run very well. So the assumption here, if you're connecting a 3-phase motor, is that it is balanced. And the only way it wouldn't be is if you had a phase miss and one winding open circuit or something like that, or a partial short circuit in the windings. So looking back at the previous slide, given that you know what the line voltage is and it's drawn a line current of 5 amps, either of those 2 slides, can we find the total apparent power? Even though we don't know whether it's connected in star or delta. S is 3 times EL times the IP. S is 3 times EP times IL, which is the same thing. So we can get to it, from that, can't we? We can say that S is hang on, that ain't the right one, that's this one. We know the line voltage and the line current, so we can use the root 3 there. It's root 3 EL IL. So that is root 3 times 440 times 5 equals. We got 3818. What are the units, Richard? 3810. Yeah, that's S. Apparent power S. Yeah, so it's volt amperes. It's what we're talking about. Sorry, it's that. Yeah, your times and volts and amps together, and it's the apparent power, it's the resultant phasor. So it's including the phase angle. And B, the total active power. We're talking about P now. So what have we found so far? We've found S. This is P. It's all about this power triangle, yeah? And that one in there is Q. And the other piece of information you've been given is that the cos of that angle is 0.8. Q is reactive power in VARs. P is active power in watts. And S is apparent power in VA. Yeah. And they always go, so S is always the hypotenuse, P is always the horizontal one, the in-phase component, the real power, the one that's using energy. Q is this apparent one that don't do any work, that just travels backwards and forwards between. In a motor, that's calls the magnetizing current. Yeah. So now, can we use that to find P? Yeah, what you're saying is, we know that cos of the angle is equal to P over S. That's where it comes from. Yeah, cosine is adjacent of the hypotenuse. And then we can rearrange that to P is equal to S times cos the angle, which is, as you rightly say, 3810 times 0.8. What we got for that? 2286, the units are VAR, volt amps reactive. Yeah. So we didn't even need to know whether that system was in star or delta to be able to calculate those values, because we can get it from the the line current and line voltage using that formula. Yeah. Okay. So let's have a look at a solving three-phase balanced load problems. A balanced three-phase load can be considered to be composed as three identical single-phase loads. Consequently, the easiest way to solve each circuit is to consider only one phase. Right, and we're going to look at that with some examples. Okay, because from that last example, if you can find the power dissipated in one phase, if that's balanced, then you're expecting them all to be the same anyway, and therefore you only need to do one. So you can isolate one leg of the load, whether it be star or delta, and analyse that. And if you want to know the total power, just multiply by 3. Alright? So, 3 identical resistors are connected in star across a 3-phase 550 volt line, dissipating a total active power of 3000 watts. Calculate the current in each line, the value of each resistance, the total power dissipated if the same load is connected in delta. Okay, so I've made this question to show you that what I talked about on that other slide about it, although the two formulas were the same, it's not the same power if you connect the same load in a different delta or star to the same line. Okay, so what I really do recommend, even in exams when you're under pressure of time, that you do sketch the circuit. So what we've got is a system like this. There's a star point. There's our 3 loads, okay? And we know that we've got a line voltage there, EL, of 550 volts. And ST is equal to 3000 watts. And because the other thing we can take from the question is, because it says it's an 3 identical resistors, we can consider them as R, and therefore ST is actually equal to the real power, because they're only resistors. There's no inductor in there. It's not a motor, so you're not going to have any Q. P and S are in phase with each other, and therefore we can say it's in watts. That's why I've given it in watts. Alright? And we tackle that problem from knowing, first part of the problem, we can say that the total S, and we're using this formula again, root 3 EL IL. We're looking for the current, we're looking for the line current, yeah. But we've got that formula for the total apparent power. So we can rearrange that, divide by root 3 times EL, we get IL is equal to ST over root 3 EL. And then when we've done the rearrangement, put the numbers in. 3,000 divided by root 3 times 550. .15 amps. Yeah. So that is the line current. The question asked for the current in each line, so we got that. Yeah. Now, we're looking then to find R. Sorry? Sure. We're going to isolate. We want to find the value of one resistor. How much resistance is that 550 volts across? We got the line voltage. We need to find the phase voltage. Yeah. So we can first say E phase is what is it? Is it smaller or bigger than the line voltage? Yeah, so it must be line voltage divided by root 3, because root 3 is bigger than 1. That's the only way you're going to make it smaller. So that's 550 over root 3 equals 317.5 volts. Okay. Then we can go by Ohm's law. R is equal to E phase over R is the other I, yeah, I phase. Okay. And here, what I would recommend is that you do it like this. 550 over root 3. Or you do it, rather than round that figure, you do the whole thing and then round. As the final answer you're looking for is the resistance at this level, probably put it in as that fraction there, rather than that result that you've rounded. Alright? Not going to make that much difference, but in some questions it could do. Alright? So that's over 3.15 amps equals. Yeah. Yeah, IP and IL is the same. Yeah. You probably, yeah, you're right, really. You probably should have made a statement there for star IP is equal to IL. Yeah. So our resistances, yeah, we'll go for 101 ohms. Yeah. All right. So each resistor in that load is 101 ohms. Alright, I'm going to do a new slide, I think. What we're doing then for part C, as we're saying, we're going to connect those same 101 ohm resistors in delta the same 550 volt line. Yep. Now the question's asking, calculate the total power dissipated in delta. So what do you think is the best way to go about that? We haven't got line current. Or phase current. But what have we got? We've got resistance and we've got voltage. Yeah. So we can we not calculate IP from EL over R, 550 over 101 equals 5.45 amps. Yeah.
That says 306, why did you go to 101 and not 303?
Because you'd only add three resistors together if they were in series, Richard. Okay. Yeah. But what we're doing is we're kind of isolating this one part of the circuit.
Yeah, I see it now, yeah.
That end is connected to a star connected generator at some point. We didn't really consider that yet, okay? But it is, okay? So that voltage is a 500 light line. We're kind of isolating that circuit there, yeah? And analysing that, and then saying we got that 3 times, because there's the same. We got the same 500 volts between these two lines, 550 there. So we could isolate that circuit and do the same thing as 550 volts across that 101 ohms. Yeah? But it's like why we just calculated that current, okay? But that current's being produced by these two lines connected as a complicated system delta, because that line is sending some current down that load and some current down that load, and that's constantly changing, remember, it's AC, and they're not in phase with each other. Alright? So that's why this current is root 3 bigger than the current in the phase. Alright? We're isolating one part of the system. Equally, we could isolate that resistor, which is being fed by the 500 volts between this bottom phase and the top one. Alright? Don't matter which one we pick, because that's a balanced system. Yeah, okay, everyone alright with that? That's a good question. So, from the other slides, we know that we can get the total power, write it as apparent power, even though we've only got resistive load here, is 3 times EL times I phase. It's 3 times the power in each load. So that's 3 times 550 times 5.45 equals . Yep. Answer? Eight, nine, 2. VA, or actually watts in this case, because it's only resistive. Yep. Alright, so that proves we got the same load. That proves what I said about the power, total power, in that one 3,000 watts, in delta 8,000 some odd, nearly 9,000 watts. Power isn't the same, even though the formula's the same, and that's because the currents are different. Yeah, we got 5.45 amps in delta. Same load was 3.15 amps star. Yeah? Right?